Now I turn to the definition of prospect theory and incorporating a new deviation from the classical approach, being reference dependence. The other deviation, rank-dependent probability weighting, we already saw prospect theory will use it, but that's as it was discussed before. So I now have to discuss more reference dependence, how to incorporate that. Well, one aspect of reference dependence is sign dependence. That means that people treat losses quite differently than gains. People have different attitudes there. We already saw an example of that in figure 8.1.1, and maybe you remember there was a left choice situation and later a right choice situation where all the outcomes were multiplied by -1, changing all the gains into losses. And then we found for the gains, people were mostly risk averse, and for the losses, they were mostly risk seeking. So that was already an example where people behave quite differently for gains than for losses, but this indeed happens in general. Now, reference dependence means that the reference point changes and the attitudes of people can depend on it, can also change if the reference point changes. And one big change in this is due to sign dependence, of course, because if the reference point changes, then some gains turn into losses or vice versa. And then the attitude can change a lot there. So sign dependence is doing much there. In general, reference dependence could incorporate more dependencies, but I must say that in general, a general theory of reference dependence, we don't have very much. How attitudes depend on reference point, even what reference points are, still much to be discovered and understood. That's yet hard. There has been a paper by Tversky and Rabin 2006. They were the first to introduce any theory about reference points that is tractable, that you can calculate, that has some plausibility. So that was a big step forward, and many people use it. It's very popular. But there still remain problems. For instance, they were using unobservable inputs in their theory, and also they were treating reference point more like choice options in disappointment theory. I will not explain what that means, but rather like that than as reference points. So there were still some difficulties and still much to be done. So I will not present this theory in this course. In this course, I will assume from now on that the reference point has been determined, and in fact, I will keep it fixed. So only for one fixed reference point, I will define prospect theory and discuss things. So I can still discuss sign dependence, and we'll do that a lot, but no other comments on reference point in this course. Also, we don't have time, not so much to do. So from now on, we assume one fixed reference point. And with that understood, I'm going to put up the definition of prospect theory. And first, I'm going to present the definition to you only from a mathematical perspective. I will give the definition, tell you which formulas to use, but I will not yet try to have this homeomorphism in, that it's psychologically plausible. That will only come after. And in fact, that was prospect theory is a masterpiece from that perspective. So I will explain it later, but not now, not at first. So now come mathematics. So we are in the context of decision-making under risk with probability distribution over money and preference relation over those prospects. And prospect theory says there exist a lot of things. There exists small u, capital U, and lambda, and they are related to each other in the way that I already explained. So that's already explained to you. And further, there's probability weighting, but it can be different for gains than for losses. For probability weighting for gains is W plus. For losses, we have W minus. And then, let us put up a general prospect, so probability distribution over money. As we did with rank dependence, we take a complete ranking of the outcomes. I write it here, but we do a bit more. Now, the signs of the outcomes are also important. We specify it in the formula. So let's assume that x1 up to xk are greater equal 0 and the others are less than equal to 0. As you see, I'm using weak inequalities here, not strict. So, and that's a nice flexibility, and we saw it before with rank dependence. And again, there will be no logical problem. You can trust me, just take my word for it. So we can this gives us more flexibility, and we just do it. We can do what we want, we need not worry about it. It also means that if there are several outcome xj that are 0, then we can choose where k is. It's free to choose, and again, we can do as we like. It will never give problems. So now I tell you the prospect theory value of that prospect x is a summation like we saw before. We saw this before, a convex combination of the utilities and then those decision weights by I yet to be determined. they will be a bit different under prospect theory than they were before. But I should say, this is not a convex combination. The decision weights need not add to 1. They can sometimes add to more than 1 or less than 1. And maybe if you hear it, you start to get worried because the old psychological literature had such formulas and they were bad and they were not aware of it. We got anomalies, discontinuities, foundation of stochastic dominance. Then this deep insight for Quiggin was that you should let the decision weights always sum to 1, then you avoid these problems. And all of that is true, but now Kahneman and Tversky went beyond it because they don't fully satisfy the rule that Quiggin proposed, but they do it in a clever manner. It turns out that they do it in a way that they are not violating stochastic dominance. That's a fact, mathematically speaking, it's very subtle. When they introduced the theory in 92, I was already doing research. I was already around. I was mathematically trained. When I first saw the formula, I thought, oh, you're the psychologist again. Of course, they're going to get trouble. This can never work. And then later I started to no, it does work. They do it the right way. I was very surprised that you can have ways that don't add to 1, still is no anomalies. So that was a deep invention, a deep mathematical improvement, novelty that Kahneman and Tversky had. And now I'm going to present to you the definition, what they did. First, if we have gains, I less equal k, then things are as usual with rank dependence, only the W plus function is used. So the decision weight of outcome xi is then, you see, I wrote here the outcome probability of outcome I and then the rank, so the probability of getting something ranked better. So this pair is then a rank probability, and the decision weight, we saw all these things before. It's what we saw before, only with W plus. So the marginal W plus contribution of the outcome probability to the rank, well, you heard it before, business as usual. For losses, we will proceed a bit differently. So now we turn to losses j bigger than k. And then I write here the decision weight. And now you see, here I write the outcome probability, but here I'm writing the loss rank, the probability of getting an outcome rank worst. So I'm doing, maybe you remember the previous meeting, there was this critic of rank-dependent utility. It said you better work with loss ranks than gain ranks, or ranks I use those terms interchangeably, but better work with loss ranks. Then we said it was a big fuss about nothing, it doesn't matter, you can do what you want. But now you see, in prospect theory, for losses, Kahneman and Tversky, they do what the critic said. We have here a loss-ranked probability. Then we determine the decision weight as our critic said. We take the marginal W minus contribution of the outcome probability to the loss rank, not the gain rank. Well, probably you also remember from the previous meeting, it doesn't matter, it's at your choice. You can always, if you want to work with gain ranks for losses, you take the dual of the W minus function. You can just do it. So it is at your choice. Then maybe you feel annoyed. Why do Kahneman and Tversky not do the same for gains and losses? Why something different? Why it feels like inconsistent? But it was in fact deep insight. It is this homeomorph I will explain later. That's fully going on here. This is really the best way to do it. So for now, you take my word for it. Something more about mathematics. First about Quiggin and Schmeidler. Quiggin and Schmeidler had this insight. So Quiggin did it for risk, I already told you. Schmeidler did it for the more general, more subtle, more difficult context of uncertainty, independently of Quiggin. I will explain later what Schmeidler did, but it was quite like Quiggin did rank dependence. So they invented this functional, they had this deep insight that functional works well. It's a good mathematical formula. But later it was discovered that such functionals had existed before in the mathematics literature. The rank-dependent functionals of Quiggin and Schmeidler, they are in fact Choquet integrals. And already in the 1950s, they were available in the mathematical literature. So if I tell it like this, then you think, so Quiggin and Schmeidler did not really invent something new, it already existed. They simply applied Choquet integral in decision theory. What's the big deal? But I think still Quiggin and Schmeidler had deep insights because they understood that exactly that is needed in the decision context that they were working. And no mathematician who knew a lot about Choquet integrals even could have had that insight. And then it's impossible for people to know all the mathematics literature. You need people with brains as strong as Quiggin and Schmeidler. When they are at that point, then they can create what they need. You can't know the mathematical literature, but they could invent it by themselves. So I still think they deserve a lot of credit and priority for their invention. Now for Tversky Kahneman, there's a similar story. So they invented a function that works well when you distinguish between gains and losses. They understood that the decision weight need not always add to 1. That can be done if you do it properly. Later, it turned out that this new functional that they had discovered had also existed in the mathematics literature before. It was a sequence integral, and it existed already in the 1970s. But again, I think still Tversky Kahneman deserve a lot of credit and priority in the same way as Quiggin Schmeidler did. Okay, going on, one of the first questions always asked in this course, it's operational split, first thing, how can you measure empirically the primitives of your theory? So also with prospect theory, let us discuss that, how it works. And if you think a little bit, you may think, well, business as usual, it's routine. For gain, we have gains, and for gains, we have in fact just a rank-dependent functional. We already know how to do it. So with gains, we proceed as we did. And for losses, it's a fact, it's dual, is what the critic said, but it's business you can understand. So for losses, we can also just measure using techniques that we know from rank-dependent utility. Then we covered both gains and losses, so we're done. So measurement is easy, nothing new really to do. Imagine that reasoning. Now, there's something incomplete in this reasoning. Something is missing. And maybe you can pause the video and think, what is missing in what I just said? And when you made up your mind, come back. Okay, I assume you made up your mind. Well, what is missing is loss aversion, lambda. If you only look at gains, and then you only look at losses, you will not find out about lambda. Lambda is the exchange rate between gain and in utility units, between gains and losses. And only if those two come if you have mixed gambles, as they call it, so where both positive and negative outcomes play a role, then that exchange rate plays a role. And it's empirically important to know and find out about it. What we said so far, treating gains and losses separately, doesn't give you any insight into lambda. So work remains to be done. So then the other things, indeed, we can measure in the way I said, but lambda, I will not tell you in general. There are papers in the literature to show how lambda can be measured in complete generality, but I only give you a simplified, pragmatic way to do it. So that's coming next. And it goes as follows. You take a 50-50 lottery, either a gain gamma or the loss -1, and then you take it such that it's equally good as the zero prospect. So you take alpha so big that you exactly get the indifference here. And now I claim it's a good approximation to say that this the money amount alpha that you need here, that is a loss aversion parameter lambda. So next I will explain why that is so. First, I write the indifference, what it means in prospect theory function. It means here we have the prospect theory value of the left prospect, and this is gain, And for losses, maybe you didn't have time yet homework, but it works like this. This is really, you take my word for it now. This is the right formula. That must be equal to the prospect theory value of the left prospect, which is the right prospect, which is 0. That equality we get. Now I cross out the weighting functions. This is pragmatic because empirically speaking, on average, the weighting function for gains and losses are not very different. And at the probability 0.5, they're usually quite the same. So it's not a bad approximation if you must be working pragmatically to assume them the same and then they cancel. So then we have that equality. Now I bring in the small u and the lambda. And there we are. The small u of alpha is equal to the capital U, but for the loss we bring in lambda. So we get that equality. And now further, I make a further assumption that it is quite okay to assume that utility is linear near the origin, near 0. For moderate amounts of money, so you must do this with moderate amounts of money, not too small that subjects are no more interested, but also not too big, so that utility is so quite reasonably linear. And then we can rewrite it in this manner. We get that equality, alpha minus lambda 0, and then we see alpha is about equal to lambda. So there we are. So this justifies this way of measuring. Empirically, we find early studies were focused on showing that lambda is important for finding big values, lambda 3 or whatever. But lambda 2, in fact, I think on average lambda 1.5, that's the prevailing empirical finding if you do balanced experiments. So roughly, people weigh losses 1.5 times more than they weigh gains. maybe 2 times, but 1.5 I think is the best estimate from the state of the literature at this moment. Now, I haven't said much about uniqueness of the functions in the functional form yet. For rank dependent in the recordings, I also didn't say much about it. The book writes about it, but let me now, for prospect theory, say a bit about it. And it holds for rank dependent utility and for prospect theory, the weighting. If you have minimal triviality, the weighting functions are uniquely determined. Then, in fact, in rank dependent utility, for the utility function, you can multiply by any positive number, but you can also add any constant that you like. That was uniqueness of utility and rank dependent utility. I already told you for prospect theory is different. For prospect, you cannot add any constant that you like. Utility must be 0 at the reference point. So that liberty you lose. But you can, in prospect theory, multiply the small and capital both by a positive constant, and nothing changes. All the prefixes are unaffected by it. So that uniqueness you have. People call that the ratio scale. And then the loss aversion parameter, how is that determined? It's a bit the decomposition of capital U into small u and lambda. It's a bit of a subtle question. Maybe there are some identifiability problems in complete generality. You have to add some assumptions, but on a pragmatic assumption, like I displayed there, then the decomposition is unique, and then lambda is uniquely determined. So that's about uniqueness. So now I told you the definition in mathematical terms, but I should also explain that these formulas are homomorphic, that they are psychologically plausible, and that will come in the next recording.